NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
47 years ago, a golden spacecraft no larger than a small car slipped quietly into the void, carrying the dreams of an entire planet. What began in 1977 as a bold mission to explore Jupiter and Saturn has become something far more profound. Voyager 1 is now humanity's most distant emissary, drifting more than 15 billion miles from Earth into the vast unknown of interstellar space. In 2012, it crossed the heliopause, the invisible boundary where the sun's influence ends and the galaxy begins, becoming the first human-made object to do so. Now that the NASA Voyager 1 has reached the other side, we know that it's totally not what we thought. Today, we'll zoom out and see where we are in the cosmos. Mapping the interstellar medium. Since crossing into interstellar space in August 2012, Voyager 1 has become the first and only spacecraft to directly study the interstellar medium from within. With 3 primary instruments still operational, the magnetometer, the plasma wave subsystem, and the cosmic ray detector, Voyager 1 has transformed our understanding of what lies beyond the heliopause. Contrary to long-standing assumptions that interstellar space is an empty void, Voyager's data has confirmed that it is a dynamic, highly structured environment marked by turbulence, shifting plasma densities, and magnetic irregularities. The spacecraft's magnetometer, a fluxgate sensor developed by NASA's Goddard Space Flight Center, has been crucial in mapping the local magnetic field outside the sun's influence.
Solar magnetic in any magnetic field with opposite direction annihilate and can release energy.
After crossing the heliopause, at approximately 121.6 astronomical units from Earth, or about 11.3 billion miles, Voyager 1 began detecting unexpected changes in magnetic field direction and strength. These magnetic anomalies suggested that the sun's magnetic field was still interacting with galactic forces beyond the heliosphere in ways scientists had not anticipated. The magnetometer recorded fluctuations and sudden shifts. These fluctuations redefined our understanding of the cosmos altogether.
In a certain particular tone. Literally, they're the sounds of interstellar space.
Complementing this data, Voyager's plasma wave system has provided an acoustic-like map of interstellar space. The plasma wave subsystem, built at the University of Iowa under Don Gurnett, monitors the frequency of plasma oscillations, allowing researchers to measure the electron density of the surrounding medium. One of the most significant discoveries came in 2013, when, months after crossing the heliopause, Voyager detected an oscillation triggered by a solar outburst that had traveled outward and disturbed the interstellar plasma. The oscillation's frequency allowed researchers to calculate the plasma density, which was substantially higher than the near vacuum inside the heliosphere. This single event was key in confirming Voyager's entry into interstellar space. Another major contribution came from the cosmic ray subsystem, which has been operational since launch and is now helping researchers chart the density and composition of high-energy particles outside the heliosphere. This instrument, developed at the University of Chicago, has detected a marked increase in galactic cosmic rays since crossing the boundary. Inside the heliosphere, the solar wind shields Earth and other planets from many of these cosmic rays. Voyager's detection of a 9% rise in cosmic ray intensity served as further confirmation that it had left the solar bubble and entered the more exposed galactic environment. Perhaps most striking is Voyager's revelation that the interstellar medium contains weather-like phenomena on a scale incomprehensible to Earthbound observers. Scientists have identified interstellar cloudlets, which are localized, high-density regions of plasma that Voyager passed through in 2020 and again in 2022. These cloudlets, likely just a few hundred astronomical units wide, caused sudden shifts in plasma density by factors of 2 to 3.
So today we're going to talk about plasma, often called the fourth state of matter, of all of the visible matter we can see in the universe.
Additionally, the spacecraft has recorded large-scale filaments, or extended structures resembling cosmic rivers of charged particles, as well as signs of shock fronts caused by supernova remnants. These findings suggest the interstellar medium is not static, but in constant flux, shaped by ancient stellar explosions, magnetic turbulence, and gravitational forces. One of Voyager 1's most enduring contributions is the realization that the space between stars is anything but featureless. Earth-based observatories and space telescopes like Hubble or the Chandra X-ray Observatory have hinted at the interstellar medium's complexity, but none have been able to sample it directly. Voyager 1, launched nearly 5 decades ago, now functions as a remote sensor embedded in that cosmic terrain. Each signal it sends, traveling over 22 hours to reach Earth at a data rate of just 160 bits per second, carries unprecedented information about a part of the universe never before touched by human technology. But wait, there's more. The local interstellar cloud and the local bubble. Voyager 1 has confirmed that our solar system is currently embedded in a region known as the local interstellar cloud, a relatively dense pocket of gas and dust, nestled within a much larger structure called the local bubble. The local interstellar cloud, also known as the local fluff, is approximately 30 light-years wide and has a density of about 0.3 atoms per cubic centimeter, significantly denser than the surrounding regions of the local bubble, which may have densities as low as 0.05 atoms per cubic centimeter. Voyager 1, using its plasma wave subsystem and magnetometer, has detected these density variations directly by measuring electron plasma oscillations and magnetic field fluctuations as it travels deeper into interstellar space. NASA scientists believe the solar system has been moving through the local interstellar cloud for roughly 60,000 years, and may exit it within the next 10,000 to 20,000 years. This cloud is not uniform. Its density and magnetic strength vary considerably, contributing to a patchy and irregular structure. The local interstellar cloud itself is just one small feature within the local bubble, an enormous cavity in the interstellar medium that spans roughly 1,000 light-years in diameter. This bubble was carved out by a series of supernovae that occurred around 10 to 15 million years ago, originating from now extinct massive stars in a region that once belonged to the Scorpius-Centaurus OB stellar association. These supernovae blasted away the dense interstellar gas that previously filled the region, creating a vast, hot, and low-density void filled with thin plasma, the walls of the local bubble. Its boundaries are denser regions of gas and dust, effectively forming a shell that separates it from adjacent cavities in the interstellar medium. This bubble is not empty. It contains several well-known star systems, including Alpha Centauri, Sirius, Procyon, and Altair, all located within the local bubble. The Sun's motion through this environment at approximately 450,000 miles per hour,
for example, here's the Sun, and here's where the Earth is, about 1 centimeter away,
or 720,000 kilometers per hour, means it is continuously interacting with the ever-changing conditions of this interstellar cavity. One important effect of being in this bubble is how it alters the permeability of cosmic rays. Voyager's cosmic ray detector has observed changes in cosmic ray intensity that correlate with the structure of the bubble and the presence of denser or magnetically shielded regions such as the local interstellar cloud. The interaction between the solar system and its galactic environment also influences the heliosphere, the protective bubble formed by the solar wind. As the solar system moves through different regions of the local interstellar cloud, changes in external pressure from the surrounding interstellar plasma can alter the shape and size of the heliosphere. A denser or more magnetized region in the local interstellar cloud, for example, may compress the heliosphere, reducing its ability to shield the inner planets from galactic cosmic rays. These interactions may have subtle but real effects on Earth's climate and radiation environment over geological timescales, possibly affecting everything from atmospheric chemistry to biological mutation rates. Thanks to Voyager 1, scientists can now directly measure the properties of these surrounding interstellar structures rather than relying solely on remote sensing or modeling. As the Sun continues its orbit around the Milky Way, completing one revolution every 230 million years, our solar system will pass through many such interstellar regions. Voyager's findings serve as a crucial baseline for understanding how these galactic environments shape the evolution of planetary systems, the heliopause, and beyond. Voyager 1's crossing of the heliopause in August 2012 marked humanity's first direct venture into interstellar space. But the data it continues to transmit has revealed that this boundary is far more complex and dynamic than once imagined. The heliopause is not a fixed or smooth shell encasing the solar system. Rather, it is a fluid, constantly evolving interface between the solar wind, a stream of charged particles emitted by the Sun, and the interstellar plasma that permeates the space between stars.
Tsunami, it finally got to where Voyager is. It caused the plasma to react in a way that it could be sensed.
The Sun and its planets are constantly encountering new regions of interstellar space, each with different densities, plasma pressures, and magnetic field configurations. As a result, the heliopause is not a clearly defined shell, but a shifting boundary shaped by external and internal forces, sometimes stretching outward when solar activity is strong and retracting when the pressure from interstellar plasma increases. Voyager 1 provided groundbreaking measurements that confirmed the heliopause lies at a distance of approximately 121.6 astronomical units from the Sun, though this can fluctuate depending on conditions. One of the most remarkable discoveries made shortly after the crossing was a dramatic spike in plasma density, as measured by the spacecraft's plasma wave instrument. While Voyager's direct plasma sensor had failed years earlier, scientists were able to detect ambient electron density by measuring the frequency of plasma oscillations caused by solar eruptions. The jump in density was a critical confirmation that the spacecraft had truly left the Sun's domain. Equally surprising was the behavior of magnetic fields beyond the heliopause. Based on earlier models, it was expected that the magnetic field direction in interstellar space would differ significantly from the orientation of the heliospheric magnetic field. However, Voyager 1 initially detected only a small change in field direction after crossing into interstellar space. This challenged long-held assumptions and prompted researchers to reconsider the configuration of both the heliospheric tail and the galactic magnetic field. In subsequent years, further data showed more complex and layered magnetic field transitions, suggesting that the interface region is shaped by instabilities, turbulence, and reconnection events between solar and interstellar magnetic lines. These findings imply that the galactic magnetic field, believed to span hundreds of light years and influence the formation and orientation of interstellar clouds, is far more tangled and dynamic than once believed. Rather than being smoothly aligned across vast distances, the field appears to be distorted by the shockwaves of ancient supernovae, local gas flows, and interactions with the magnetic boundaries of stellar systems like our own. Voyager's instruments have picked up twisting and fluctuating magnetic field lines, offering a rare glimpse into the energetic processes that govern the galactic environment. Understanding the structure and variability of the heliopause has real implications for Earth and the rest of the solar system. The heliosphere acts as a shield against galactic cosmic rays, which are high-energy particles that originate outside the solar system. Changes in the shape and strength of this shield directly affect the radiation environment in space and, by extension, influence the safety of astronauts, satellite systems, and even atmospheric processes on Earth. As the Sun's activity ebbs and flows on its 11-year solar cycle, and as the solar system encounters new pockets of interstellar material, the boundary conditions of the heliopause and our cosmic protection continue to evolve. With Voyager 1 still transmitting faint signals across more than 15 billion miles, scientists now sit in the front row seat to this ever-changing frontier. Its observations have revolutionized our understanding of the boundary that separates us from the broader galaxy, showing that even at the edge of the Sun's influence, space is not empty but alive with movement, structure, and complexity. Earth's connection and the golden record. Although Earth is protected by both its magnetic field and the heliosphere, changes in interstellar conditions subtly but significantly influence the planet's long-term climate and biological history. One of the key mechanisms by which this occurs is through the cosmic ray flux of high-energy particles originating from outside the solar system. These galactic cosmic rays, composed primarily of protons and heavy nuclei, penetrate the solar system and are partially deflected by the solar wind and magnetic fields. However, their intensity at Earth varies as the Sun moves through different regions of the interstellar medium, and these variations may have broad implications for climate, evolution, and technology. Cosmic rays interact with Earth's upper atmosphere, causing ionization of atmospheric molecules, which in turn can lead to increased cloud condensation nuclei, which are tiny particles around which water vapor condenses to form clouds. Cosmic rays can influence low-altitude cloud formation, which plays a crucial role in regulating Earth's temperature by reflecting incoming solar radiation. Though not the dominant driver of climate change, fluctuations in cosmic ray intensity may have acted as subtle modulating factors in Earth's climate across glacial and interglacial cycles. As Voyager 1 has confirmed, the heliosphere, our Sun's protective bubble, does not offer a constant level of shielding. Its size and strength vary depending on both solar activity and the density and pressure of the surrounding interstellar medium. During periods of low solar activity, such as solar minimums, the heliosphere contracts and becomes less effective at deflecting galactic cosmic rays. Similarly, as the Sun traverses denser or more turbulent interstellar regions, such as cloudlets within the local interstellar cloud, the heliosphere is compressed, allowing more high-energy particles to reach the inner solar system. According to models, the Sun completes an orbit around the Milky Way every 225 to 250 million years, and in the process, it passes through different interstellar medium environments every tens of thousands of years. One such historical event may have occurred approximately 2.6 million years ago. This period also coincides with the onset of Earth's most recent ice age. Another long-term consequence of increased cosmic ray exposure is its potential impact on genetic mutation rates. While Earth's atmosphere provides substantial shielding, cosmic rays can still cause DNA damage in organisms, particularly those in high-altitude or space environments. Over evolutionary timescales, periods of elevated cosmic radiation could contribute to accelerated mutation rates, influencing natural selection and genetic diversity. Some researchers have speculated that this mechanism may have played a role in both speciation events and extinction episodes. Modern concerns also extend to technological systems and human activity in space. When cosmic ray flux increases, satellites and spacecraft electronics are more vulnerable to single-event upsets or sudden failures caused by energetic particles. For astronauts aboard the International Space Station or future missions to the Moon and Mars, heightened radiation levels pose significant health risks, including elevated cancer rates and central nervous system effects. Space agencies like NASA and ESA use real-time space weather forecasting, partly informed by Voyager and other heliospheric data, to assess and mitigate these hazards. As Voyager 1 continues to report from the fringes of our solar system, it deepens our understanding of how cosmic rays, filtered and modulated by the heliosphere, ultimately reach and influence our planet. But it's not just a one-way mission. The Voyager 1 also carries the golden record, a gold-plated copper disk that was curated by a team led by astronomer Carl Sagan of Cornell University. It serves as a message to any extraterrestrial intelligence that might one day encounter the spacecraft, presenting a snapshot of Earth's cultures, ecosystems, and scientific understanding in a medium designed to last over 1 billion years, even in the harsh radiation and vacuum of interstellar space. The record is encased in an aluminum protective cover, electroplated with uranium-238 for potential radiometric dating, and designed to withstand both micrometeoroid impacts and the cosmic rays it will encounter in deep space. The contents of the Golden Record are a blend of human achievement, natural wonder, and cosmic orientation. There are 116 images encoded in analog format, ranging from mathematical definitions and DNA structure to photographs of a mother with her child, cities, animals, and geological features. The intent was to represent the diversity of life and culture on Earth, and to convey a sense of our civilization's intellectual and emotional depth. These images are accompanied by a rich audio collection that includes greetings in 55 different languages, from ancient Sumerian and Akkadian to modern Urdu, Mandarin, and English. Each greeting begins with "hello" or "peace," embodying a tone of hospitality and curiosity rather than conquest. One of the most remarkable inclusions is the musical anthology, spanning both time and geography. The playlist features 27 musical selections, ranging from Johann Sebastian Bach's Brandenburg Concerto No. 2 to Chuck Berry's Johnny B. Good, a spirited nod to 20th century American culture. Also included are traditional songs from around the globe: Senegalese percussion, Japanese shakuhachi flute, Peruvian panpipes, and a wedding song from the Zuni tribe of North America. Each track was chosen not only for its artistic value, but also to showcase the global nature of human expression. Natural sounds, what Sagan called the audio biography of the planet, were carefully recorded and layered onto the disc. These include the sound of wind, thunder, rain, a volcano, and even the rhythmic beating of a human heart, a baby's cry, the roar of a train, and the calls of animals like elephants and whales are part of this sonic mosaic. Perhaps the most scientifically significant feature of the Golden Record is its pulsar map, which is a diagram that pinpoints Earth's location using 14 pulsars. Each line on the map extends to a pulsar and is labeled with its period expressed in binary, which gradually changes over time. Any intelligent civilization that finds Voyager could theoretically determine where and when the spacecraft originated. In addition to the contents themselves, instructions for playing the record were etched onto the cover in symbolic diagrams, including how to build a stylus and interpret the analog audio and video signals. These were designed under the assumption that math and physics are universal languages, even if verbal language and symbols are not. So, what's next for Voyager 1? Its continued transmission from over 15 billion miles away shows that long-term missions are not only possible, but transformative. The spacecraft's endurance informs next-generation initiatives like Breakthrough Starshot, while its data reshapes how we understand our galaxy's outer reaches. As its trajectory leads it toward Gliese 445 over the next 40,000 years, Voyager is humanity's quiet envoy to the stars. Long after its power fades, its golden record will endure as our first message to the cosmos, awaiting discovery in the infinite dark. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.